Hello student to the foundation of classical electrodynamics course. So, under module 2 we are today having lecture 46 and we will like to continue the electrostatic boundary value problem that we started in the last class. We have class number 46. So, now we are dealing with this two-dimensional problem, two-dimensional Laplace's equation. So, today we will solve a two-dimensional Laplace's equation for spherical coordinate. So, Laplace's equation for spherical coordinates. So, for spherical coordinates the Laplace's equation is simply r theta phi and then it will operate over some potential big phi is equal to 0. That is the form. If I now explicitly write this operator, it should be 1 divided by r square del r and then r square del phi del r plus 1 by r square sin theta and then del theta and then sin theta del phi del theta and finally plus 1 by r square sin square theta del 2 big phi del phi square is equal to 0. That is the form we know, right. Now, this is a two-dimensional problem. So, let us consider the azimuthal symmetry. So, this is for azimuthal symmetry. For azimuthal symmetry, what we have that phi should be independent of the variable phi. So, then this equation, whatever the equation, will simply contain. So, this term will no longer there. So, this derivative will 0. So, eventually we have, let us write equation, the differential equation. The differential equation that we have is del r, because 1 by r will cancel out. So, we have del r square del phi del r plus 1 by sin theta del theta and then I should have sin theta del phi big phi and del theta that is equal to 0. That should be my differential equation. Now, again, like the previous problem that we did in the last class, my total potential phi, which should be function of r and theta, can be written as a separation of variable like r function of small r and q function of theta. So, I just use the separation of variable, and if we put that in this equation, and then I after putting this in equation 1, one can simply have 1 divided by r d dr and then r square dr dr, because q is a function of theta. So, so this I can take it outside, and then I divide everything to 1 by r q, and then it should be 1 plus 1 divided by q sin theta and d theta and sin theta dq d theta is equal to 0. Now, this portion is simply function of r and this portion is simple function of q or simple function of theta. Then I can so this is a standard procedure. So, I can write it as 1 by r d dr and then r square dr dr, that is equal to minus of 1 by q sin theta and then d theta and then sin theta dq d theta. This has to be some constant, and this constant I write like L into L plus 1. Why I am writing this we will see later, because if you write this constant at L into L plus 1, then we have a well known differential equation in our hand whose solution is well known. So, then I can have from this, I can have the equation say 2a, one equation 2a like d dr of r square dr dr is equal to L into L plus 1 r, and equation 2b is d theta and then sin theta and then dq d theta, that portion, plus I can make a minus sign here and then put it this side, plus L into L plus 1 and then sin theta and then q is equal to 0. These two equations we have. One equation is only as a function of r and another equation is only function of theta. So, that is the I mean technique we use for separation of variable problems. Now, the general solution of the 2a one can find, and the solution, this is for your check, you can check it. The general solution of equation 2a is this: r as a function of r is equal to constant a r to the power l plus b divided by r to the power l plus 1. So, one can check it quickly by just putting this solution r to equation 2a and check that left hand side and right hand side are matching or not. Just put this value here and check left hand side and right hand side is matching or not, and it has to match because this is a solution. So, I give you students, I give you this as a homework problem. Please check that whether whatever is written here in the blue color, the solution, it is satisfying equation 2a or not. Okay, so what about 2b? So, I can rearrange these things a slight by doing all these derivatives, whatever is there, and 2b rearranging equation 2b, what I get is this sin theta and d2q d theta square, then plus cos theta dq d theta plus L into L plus 1 sin theta q equal to 0. Just to rearrange this term, I just make the derivative, whatever the derivative we are having here, d theta, and then make it the derivative, and I am going to get this. Well, now let us take x equal to cos theta. Then that leads to dx d theta as say minus of sin theta, and dq d theta by using the chain rule will simply becomes dq dx and dx d theta. Dx d theta is minus sin theta, so minus of sin theta dq dx. So, d2q dx is there. So, d2q dx square is simply d of d theta and minus of sin theta dq dx. That is simply, if I do this, so it simply comes out to be sin square theta d2q dx square minus cos theta dq dx. Why? Because I am making a derivative here, so the sin theta become cos theta, so minus cos theta dq dx is one term, and another case it is minus of sin theta and d theta of dq dx. Again I can make this d dx and dx d theta. So, dx d theta dx d theta, I can replace here this value, that minus of sin. So, minus of sin theta multiplied by minus of sin theta becomes sin square theta. Okay. So, so I put everything here in this equation, and when I replace, what I see is this. It gives me like sin cube theta d square cube dx square, and then minus of 2 sin theta cos theta d of q dx plus L into L plus 1, and then sin theta cube equal to 0. So, one sin theta will going to cancel out, So, I have sin squared theta d2 q dx square minus 2 of cos theta 2 of cos theta, then dq dx square, and then plus L into L plus 1, then q equal to 0. Now, if I put this cos theta already, so as x is equal to cos theta, so that we already took here. So, if I just replace here in terms of x, it simply becomes a very interesting equation, which is 1 minus x square d2 q dx square minus of 2 of x dq dx plus L into L plus 1, and then q is equal to 0. Now, this equation is not new. We already discussed this equation, because this is the differential equation whose solutions are given as a Legendre polynomial, and these things we discuss when we are discussing the multipole expansion. So, the general solution is then known to us, and it is QL is equal to the Legendre polynomial of x, or I should say PL of cos theta. Okay. This is the Legendre polynomial. This is the Legendre polynomials. So, the most general solution, the most general solution then becomes simply phi, which is a function of r and theta, because both the solutions is now in our hand. So, it should be summation over L tends to 0 to infinity A L r to the power L. This solution we already figure out, B L divided by r to the power L plus 1, we check it, multiplied by the Legendre polynomial, that is the solution for Q. So, P L of cos theta. So, this is the way the potential will going to vary for two dimensional case when the system is having a the spherical symmetry. So, let us do one example, say, so example, and the potential. So, the example is the potential phi 0, big phi 0, which is a function of say theta, is specified on the surface of a hollow sphere of radius r. So, over a hollow sphere of radius r, the potential is defined. Find the potential inside the sphere. Okay, so so that is my sphere, say this is a hollow sphere. So I can say this is like a cell, and in some coordinate system, and this is with radius r, and the potential here is defined as phi 0, and that is a function of theta. So when you move the theta, this is a phi symmetry, but if you move, that should be a function of theta. Now the question is, it is given at the you know on the surface, what should be the potential inside that means in this region when r is less than big R, then what should be the potential. Now let us write the general solution, because the general potential for this system is already derived, and that is this. This is the general form of the potential for any spherically symmetric system, and this solution I am going to use directly. I am not going to, I mean that's why we did it. So the solution, if I directly use here for this problem, so the general solution phi, let me write it, phi function of r and theta, that is summation over L A L r to the power L plus b divided by r to the power B L divided by r to the power L plus 1 multiplied by the Legendre polynomials, this. Now you can see that when r tends to 0 inside, then what happened, this term will going to blow up. So that means that is non-physical to you know when the potential is blowing up at r tends to 0. So that eventually tells us that B L equal to 0. Why? If it is not 0, then at this quantity tends to infinity for r tends to 0, which is not acceptable. So that is why I can, from the very beginning, I can say that B L has to be 0. So then what should be the form of the potential? The form of the potential now simply phi is equal to sum over L A L r to the power L and the Legendre polynomial P L cos theta. This is the solution. Also another boundary condition that is given, and this boundary condition is saying that over the surface, that it when r is equal to big R and theta is there, that value is theta phi 0, which is a function of theta, something like that. So I can write here that the summation L A L r to the power L, I just need to put r to big R because it is at r equal to big R, P L cos theta is simply phi 0 function of theta. That is the condition. Now now we need to find out what is the value of AL. And if you remember, in the previous day we had a problem where we used the Fourier trick. A similar kind of trick we will going to use, because we have again a very nice relationship with all these Legendre polynomials, because they are forming the complete set in function space. So, in function space they are forming the complete set. So, that is why they are having a relationship. So, that we are going to exploit. So, the Legendre polynomials now consist of a complete set of function complete set of functions in the interval -1 x 1. That basically, because this is for x, that is I am talking about P L of x. Now, if x is cos theta here, so that gives me that it should be 0, theta and pi, okay, because when it is cos theta is -1, then so when 0, then it is 1, and when pi, this is -1. So, it goes like this. I mean, this limit is like this. So, I should have, so for orthogonal set, so for Legendre polynomial for a orthogonal set, for a orthogonal set. So, if I integrate -1 to 1, one Legendre polynomial with x and another with x prime dx, which in terms of which in terms of cos theta, it is PL cos theta and PL PL prime cos theta and sin theta d theta, because x is cos theta. So, dx will be sin theta d theta. Then that value is 2 divided by 2l plus 1. Again, it should be delta L prime, like in the previous problem. This is the case. So, we have sum over AL, then r to the power L PL cos theta is equal to phi 0 as a function of theta. So, now we are going to use this trick, because we know that it is related to delta function. So, we will going to use this trick and it will be like this. So, sum over AL, which is already there, this is over L, this is over L, and then r to the power L, I can put it outside because it is nothing to do with cos theta, and then I am going to integrate 0 to say pi, and then P L prime, and then cos theta, and then I multiplied this P L cos theta to P L cos theta, which is already there, and then sin theta will be there, sin theta d theta, and in the right hand side whatever the function we are having, because I do not know, this is a function of theta which is given, which has to be supplied to find the explicit form. It should be P L prime cos theta, and then sin theta d theta. So, this quantity is forming a complete set which we discuss. This quantity is forming a complete set. So, I just mentioned here. So, that thing I go to use. So, it will be L A L r to the power L, and this part is 2 divided by 2L plus 1, and then delta function L prime. That is again equal to integration of 0 to pi, and whatever is there I just simply write phi 0 theta, and it is P L prime cos of theta sin of theta d theta. So, this is related to the delta function. So, what I do that I just integrate, and after integration we can remove this delta function, and I just write A L r to the power L prime. When L is equal to L prime, then that is meaningful, and I have 2 divided by 2 L prime plus 1, and that side I have simply 0 to pi, because we can't do anything right now because phi 0 theta is not given. This is a functional form, so it will remain like this. Okay. So I can simply have, so now I can replace, because this is a Dam index, so I can replace, and just replacing L prime to L. So, I can have A L as 2 L plus 1 divided by 2 r to the power L integration of 0 to pi, and then phi 0 functional form which is still unknown, P L cos theta, and then sin theta d theta. Now, as I mentioned that this is not given, but now I am saying if phi 0 is given, then I can execute the value of A 0. Suppose phi 0 theta is given, and this value is say k sin square theta divided by 2. So, that is the value of the potential over these, over these surface, and it is a function of theta. So, if you change the value of the theta, the potential will change. So, from here you can see that when theta is 0, the potential is 0, but when theta is say pi, the potential is k, and so on. So, there is a variation of the potential of the surface. Then what is my phi? The general solution is there, right. So, phi r theta, that is it is L which goes to 0 to infinity, then A L r to the power L P L cos theta. That value is now, we know that this was before theta 0 theta, but now I put the explicit form. So, this is k of sine square theta by 2. Now, it is very interesting treatment, because this is a function of theta in right hand side, and left hand side also I have a polynomial. So, I know the explicit form of this polynomial. So, if I have this polynomial in such a way that this sine square theta is there, so the coefficient of that quantity should be matched from both the side, and I can explain, we can find out the value of A L. So, let us do that. So, P, we know that P 0 of cos theta is equal to 1, P 1 of cos theta is equal to cos theta, and so on. So, let us expand up to these two terms, because after that we have cos squared theta and so on. So, let us expand up to this. So, summation L equal to 0 to infinity A L r to the power L P L cos theta, that is when I have L 0. So, that term I write in the right hand side, it is sine squared theta. So, that I write in form of these Legendre polynomials. So, these I write like k 0 k divided by 2, then P 0 cos theta, which is 1, and then minus P 1 cos theta. So, if I bracket it, so this is 1 and this value is cos theta. So, that is 1 minus cos theta, and so this value is equal to 2 sine square theta by 2, cos square theta by sine square theta by 2 plus cos square theta by 2 minus cos square theta by 2 plus sine square theta by 2 plus sine square theta by 2. So, it should be 2 sine square theta by 2. So, that quantity is this one. So, half, that is why half is here. So, the point is I can write this right hand side in form of this Legendre polynomial, and here I must say that any function, because these Legendre polynomials are forming a complete set in function space. So, any function can be expanded in terms of this Legendre polynomial. So, here we have sine square theta by 2. So, I can suitably adjust my Legendre polynomial. Only I can use this first Legendre polynomial, and I find that I can regenerate this function. So, now if I tally from left hand side and right hand side, then I simply have A 0 is k by 2 and A 1 is minus of k by 2 r, because A 1 r is equal to minus of k by 2. So, A 1 has to be minus of k by 2 r, and all the L greater equal to 2 has to be 0. So, my potential what I get r theta is simply k divided by 2 then p 0 cos theta minus r prime minus not r prime is r 1 divided by r p 1 cos theta is equal to k by 2 simply 1 minus r by r cos theta. That is my result here. When all these parameters are given, and I can find it that this is my result. Now, AL can also be figured out directly, because here in this formula I already write that AL can be written, and after doing this this tally I just find out what is my A1 and what is my A2, A01 and then 2 etc. So, this I just expand right hand side in the term of Legendre polynomial and then find, but still we can find AL directly. So, if I do that, finding AL directly. So, what I have here is AL is equal to 2L plus 1 divided by 2 r to the power L integration 0 to pi, and then we have phi 0 theta and then PL of cos theta and then sin theta d theta. This is what we had here, right. So, now theta big phi 0 theta in explicit form is given, it is k 0 by 2 1 minus cos theta, it is k 0 it is k multiplied by sin squared theta. So, that I write in this, that we write in this form. So, my A 0 is what then? Yeah. So, my A 0, when I put L equal to 0, then it should be half integration 0 to pi and then k divided by 2 1 minus cos theta, and then this is L p 0 is 1. So, 1 and then sin theta d theta, right. So, these integration if I execute. So, let us put this k by 2 outside. So, we have k by 4, then integration 0 to pi sin theta and then minus sin theta and cos theta, right, that over d theta. This is a very straightforward integration, and I can have k by 4, and then this integration is minus of cos theta, that we need to execute at 0 to pi, and then minus of half of then sine, so another half will be there, it will be sine 2 theta, and then it will be cos 2 theta, so it will be cos 2 theta and with a negative sign, so this should be plus, and 0 to execute at this point. So this value when we execute 0 to these things, and it simply gives us a0 as k by 2, and this is cos theta, minus of cos theta. So when we put pi, it should be minus 1 and then minus 1, so it should be minus of 2 plus, and then when you put 0 then 1 and then 2 pi is 0, so 1 by 4, so it is simply 2, so I should have it is k divided by 2. Now a0, if you look here, already we figure out with the expansion that it is a0 by 2. In the similar way, if you calculate a1, I am not going to do the full calculation, you just it should be 2 plus 1 and 2r, and the integration is 0 to pi, and it is k by 2 1 minus cos theta, and then cos theta and sin theta d theta, because we have p1 cos theta is equal to cos theta, that we put here. Now if you execute this integral, then you will going to get the same value like minus of k by 2r, which we derive here this. So I am not going to do the entire integration, I have already shown that from this equation, whatever the equation you get, you can directly find out AL. So there are two ways we calculate and show that how to calculate these constants. A0 I calculate, and A1 again you can calculate by executing this integral. This is not a very big deal to do this integration. So if you do this integration, you will find a result like k by 2r. Well, today I like to conclude here because my time is limited. So in the next class I will try to do few more problems regarding the boundary value issue, and another technique like image method, that is important. We will not going to do very detailed, but few problems I like to show that how it works and these things, and then we are going to start maybe after next day's class we will start our third module where we will start the magnetostatic. So thank you for your attention and see you in the next class.